So we are going to move on now to Ralph McNutt, who's going to talk about this future architecture complexity trade that he's driven with some support from others here at the team. Ralph, it's all yours.
Okay, thanks, Michael. Well, this is sort of prequel part 2 to where we are currently now. Got to have the next slide, please. What I just wanted to do is to give everybody a little bit of a feel for what we did in trying to cast a very, very wide net to make sure that we really did have a notion of globally what the capabilities look like for using the SLS and for using the various stages that were available out there to use. Basically, we set up a tool where that one could input the observatory mass, the observatory configuration, and select the kick stage, including with these all the various margins and reserves that would be appropriate on the masses to try to be able to do an apples to apples comparison of what one could do with all of the various launch combinations that we took a look at. Next, please. So there are a lot of mass leans on the various options. On options 2 and 3, for example, one has to worry about and Jim alluded to this, one has to worry about keeping these solid rocket motors from getting too cold. You have to also worry about having to keep the minimal gradients across the solid rocket fuel. And again, we dug into this. In this particular case, we looked at actually using the waste heat from the RTGs to move that around. Basically in a blanket configuration to deal with that. One could also think about using electrical heaters as well. It's another configuration we looked at. In any event, this is going to add some more mass. Next, please. We also looked at other mass leans that had to do with having appropriate adapters, because one has to be able to worry about the adapters which can actually on the Earth actually carry the mass of everything above those. These are going to increase the amount of mass that I have to carry. This is all taken into account for option 1, where that I'm using all of the stages during the Earth launch. But for option 2 and 3, where I'm carrying a solid rocket motor with me, I have to out into deep space. I have to worry about doing the right bookkeeping on those. Next, please. There's other mass leans as well. Jim Kinnison also alluded to the interstage on the solar orbit maneuver for providing guidance and control and an attitude control system. Also, we took a very close look at all of the various pieces of a control thermal system. There's a thermal protection system, basically that's a carbon shield, a structure assembly to hold those. There's 3 additional shields, and then a balanced mass and structural support. And again, we looked at those in some depth on all of these various configurations, along with appropriate contingencies and unallocated mass reserves. Next, please. And no, I'm not going to read all of this, but this basically outlines the study approach. And again, these slides are going to be available. Suffice it to say that in dealing with the solar orbit maneuver, we had to go through it a very logical step-by-step proposal to try to or approach in order to try to put things together. At the beginning of the study, we actually took a look at a more primitive kind of a thermal shield and used the New Horizons spacecraft as a model. At the same time, we had some of our partners were looking at ultra-high temperature materials to bring the shield masses down. And so we worked the kinks out of the model originally with a more primitive thermal shield, which was a lot heavier, and then circled back once that the new information had come in, which does indeed bring the thermal shields down, but again does not solve all the problems as I alluded to in the previous talk. Next, please. And this just gives the solution methodology of how that we went through step by step. We basically had a series of mechanical designs for the spacecraft for a set number of perihelia, and then did all the appropriate orbital calculations. In this case, trying to get upper limits as a function of the various injected mass. And then this led us to the point design that Jim Kinnison and the other engineering team used as a basis for the more detailed calculations. So what we did originally was try to find upper limits and then go back and look at the sky maps for those particular cases, double check the results, and see what that looked like as you got off of the ideal conditions in the plane of the ecliptic for trajectories. Next, please. This graphically shows what we did. We actually took, for the solar overbreath maneuver, a separated observatory mass of about 900 kilograms. This is consistent with what Jim was talking about earlier, and specifically looked at the inner stage, the smart stage avionics, the shield, the supports, the ballast, the thermal blankets, the adapter to the observatory, the adapter to the previous stage, and a 30% unallocated reserve. One can look at the nominal minimum C3s for various perihelia, and we looked at those from 12 solar radii down into actually 2 solar radii. The graphic shows that, for example, we, in looking from 6 solar radii down to 2 solar radii and 1 solar radius steps, we looked at configurations for the Orion 50XL, the Star 48GXV, and the Star 48BV, getting masses for each of these configurations so that we could do a detailed comparison. And you can see as you go down from 6 to 2 solar radii how that the actual thermal shield increases in size. Next, please. So we made a lot of we looked at best trajectories for the nominal observatory mass assumptions. And again, option 1, a separated observatory mass of 860 kilograms, option 2, 930, and then option 3, 900, plus the 200 kilogram interstage and other things. And Jim mentioned earlier that stack mass all together came out to about 7 metric tons. And I'll show a little bit more on that again once one puts in all the thermal shield mass as well. Next, please. So the best trajectories for sort of the nominal observatory mass, the best case that we got using this limiting process was in this case for option 2 with a burn out at Jupiter, escape speed and here of about 7.8 kilometers per second. This is with a Centaur plus a Star 48 GXV. Time to 400 AU is about 52 years. There were 4 more option 2 cases that were coming in with times out to 400 AU of about 51.8 years to 52.34. So these were all very closely spaced. And that was true of a lot of a majority of these cases. The next thing that came in was the best option 3 case. In this case, we were at 52.73 years. This is with a Centaur 3. And you actually, in this case, using an Orion 50XL, a much larger solid, and going into 2 solar radii. So this was even a heavier thermal shield stack than what we've got for the baseline that we did the detailed calcs on. And then finally, there was another option 2 case, and then we finally got down to the best option 1 case, but again, something that has the least amount of risk. And this was the Centaur with the Star 48 BV, and again, the baseline heliosphere case that Jim and the other engineers were talking about earlier. This gave us a time to 400 AU of about 53.8 years. So you can see that spanning these best cases across the various options, it goes from about 51.5 years to about 54 years, which is not much of a difference. And yet, as we go from option 1 to option 2 to option 3, we're increasing the likely cost as well as the risk significantly. Next, please. And this is just shows some of the other numbers that come in with this. So basically, the injected mass for option 1 ends up with being about 3302 kilograms. Option 2 about 4470, and then option 3 in this case with the Orion 50XL about almost 8 metric tons. So this is pulling in all of the additional things that one has to worry about in addition to just the bare observatory. Next, please. And so we actually went through and had we had a lot of different configurations. I've got the number on the next page. I think we looked at 181 different configurations that one could put together. This shows a blow up that gives the time to distance in years. This is going from 0 out to, I believe, out to 10 years, the first 10 years of flight, and going from 0 out to 30 AU. You can see that there are two different families, and this was also mentioned earlier, that where one family of the option 1 and option 2 cases start from Jupiter's orbit, so they have a start time advantage. They are slightly slower. And the slowness is given by how much that the curves tend to go upward. All of the option 3 cases, the last gravity assist, of course, started near the sun. And you can see that some of those actually start overlapping the option 1 and 2 cases as you go out. They're not as bent upward as much, but it takes time for them to keep up. And actually the differences in the velocities are not that great. Next, please. And this just shows a blow up going out to much larger distances and larger times. And basically with this simple analysis, we could get to about the fastest case here was getting to about 375 AU after about 50 years of flight. This is from the, and this is what's plotted here are the 109 solutions out of the 174 cases we examined for an 860 kilogram spacecraft. We also looked at spacecraft masses slightly above that and all the way down to 200 kilograms. And qualitatively, these are all the same. Next, please. Okay, so you could worry about, well, how accurate are all of these and did we make any mistakes? And so my colleague Vikas went back and redid all of this in MATLAB because the original calculations were all done with an Excel spreadsheet. And it turns out that he ended up getting, for several cases, not all of these, but for quite a few of them, representative got, again, parameters that were consistent with what that the previous analysis had done. Next, please. And again, this shows the same kind of behavior. In this case, this is a more traditional distance in astronomical units versus years. You can see this a little bit better. The inset at the top again shows the trajectories at the top are from the option 3, and the ones that are, I'm sorry, the ones at the top are from option 1 and 2. They start out at about 5 AU. And then the ones toward the bottom, the red lines are the option 3 solar Obirth maneuver. And then in the bigger plot, you can see that, again, as you start going out, the curves start intermingling because the solar Obirth maneuvers tend to go a little slightly faster, but they got off to a lower start. And so it turns out that after 50 years, the option 3 scenarios don't really cover much more distance than the option 1 or option 2 scenarios. Next, please. And we took a really close numerical look, and again, for the various solutions, everything converged and was quite accurately. A few differences because of some numerics, but this gave us a good additional check on the system to make sure that we hadn't missed anything in putting all of this data together. Next, please. So again, basically this just shows, it talks about what was done in putting this tool together, going back, and we'd started with something quite crude in Excel 4 years ago now, and this just all verifies all those calculations, gives us a better tool for generating graphics by using MATLAB as well. And the next one, please. And that's it. So at least it gives you a little bit of an idea of what we've done and how wide of a net that we have thrown. We could also, if we have data on other launch vehicles, those could be incorporated as well. Thank you.
Thanks. Thank you, Ralph. We've got about 3 minutes for questions if anybody wants to ask Ralph more about this analysis. It was very interesting to me, Ralph, to go from the discussions we had at the beginning of this study, where I had feelings about whether or not the extra cost of the Obirth maneuver hardware and risk and so forth, as Jim talked about earlier, whether or not all that extra cost would be worth the extra science that we would get out of it. I did not quite, I wouldn't have put my money on the idea that not only would it cost a lot of extra money and incur more risk, but it wouldn't actually be that much faster over the course of the baseline mission. That was unexpected to me, but the numbers are bearing that out quite clearly.
Well, I was a little surprised as well, but part of the issue, Michael, and for everyone out there, is that again, and I alluded to this earlier, while the solar over-Earth maneuver has been cited and touted a lot as being a solution, this is really the first time that there's been a detailed engineering design trade study that's been done. And again, these are the same people that worked on the thermal shield for Parker Solar Probe, augmented by some other people out there that have, taken the state-of-the-art past where we were with when Parker was developed. And it's just not in the cards. And I think that this is actually a very important result that's come out of the study.
So Nibbin has actually asked us, why not employ Adept Spiderweave 3D woven carbon fabric instead of your thermal protection system? This can save the size consumption as well as offer greater thermal protection to heat shields. Could you just talk a little bit about the thermal testing that we did on those advanced materials?
Well, carbon's part of this, and again, this gets back to having ultra high temperature materials that were actually tested up to over 3,000 degrees Kelvin. The problem is that once you get inside of about 3 solar radii, the temperatures are so high that the vapor pressure of pure carbon literally goes through the roof, and you just basically sublimate the carbon away. And so there's some new materials out there that incorporate the use of metal carbides, which do not end up having such a large impact on the mass. So actually, these thermal shields that we've got are actually on the order of the mass of what you would have with pure carbon. But there's a means of actually keeping the vapor pressure down so that you can build something out of them. A lot of the structure that's involved here is literally the structure holding the carbon shields in place. And so again, you have to really do a proper mass accounting of all of this, and which is the reason that, for every one of these various rocket motors and various distances, it really took a different mechanical design. So this is but it was a very detailed piece of work, but I think that it was well worth the investment.
And we're going to cover a great deal of that in the report itself when it comes out.
Exactly.
And it was really interesting for me as an engineer to be looking at this and not just run into engineering questions, but to start to run into those hard limits of physics on the materials. So, all right, everybody, we are at 12:30. I'm sorry, we're at 12 o'clock, and we have a break from now until 12:30. When we come back, we will have Rob. It says John Blevins on the schedule. He's not able to join us, I understand, but Rob Stoke is going to present to us on the NASA Space Launch System. Join us again at 12:30. Have a good break. Get up, stretch, refresh yourself, and we'll see you again soon.